mathematical expressions, we are going to do exactly the same thing we would do with multiplying numbers or multiplying binomials. As you can see from these exercises right here, we have products of binomials. All right. And well, the first one, it's a simple case. We're going to do, what's that? The square root of 3 multiplied by 5. And in this case, the square root of 3 times the square root of 30. Okay, what are we going to do here? So that's going to be 5 times the square root of 3, for which there's nothing to simplify any further. That square root of 3 remains the way it is because 3 is not a perfect square. And well, however, for the next multiplication, check this out. That's plus square root of 3 times square root of 30. And whenever you have something like this, what we do is use a product rule for radicals, and the radical of a product is, the product of two radicals by the other way rather is, first of all, 5 root of 3. It's going to be the radical of a product between two numbers. All right, and well, when simplifying this number, so that's 5 root of 3 plus 3 times 30. That's is that a 90? That's 90. And well, it turns out that we can simplify that square root of 90 because, do you see it?
9 and 10.
9 and 10. And in fact, one of those factors happens to be a perfect square. So that'll be 5 root of 3 plus square root of 9 times 10. Take the square root of 9, which is 3 outside. Right, take the square root of 9, which is 3, and times the square root of 10. And in this case, can we combine this like this? For instance, that's 5 plus 3 equals to 8. Root of 13, can we do this? No, we can't do that. So final answer, it's 5 root of 3 plus 3 root of 10. And the reason why we can't combine these together is because, yes, these radicals have the same index. However, the condition is not just to have the same index, but also the same radicand. That is the same quantity inside of the radical. All right, let's have a look at another one. Let's see. So, square root of 5 minus square root of 6 times the square root of 7 plus 1. And in this case, well, we're going to use the FOIL method to distribute the two groups of parentheses. We're going to do the square root of 5 times the square root of 7. And then the square root of 5 times 1. So from here, what we're going to get is, well, number 1, the square root of 5 times the square root of 7. So leave it as a product for a second, and then let's do the square root of 5 times 1, that is the square root of 1. The square root of 5 times 1, which is just the square root of 5. And then, well, let's do the distribution for the second part of the foiling, that is the square root of 6 times the square root of 7, and negative root of 6 times 1. That'll give us minus, first of all, square root of 6 times the square root of 7. And on the other hand, negative square root of 6 times 1, which is just negative square root of 6. Right? Okay, so let's see if we can simplify anything by any chance. So the product of the radicals is going to give us the radical of a product, that is the square root of 5 times 7 plus this root of 5 is simply root of 5 minus the square root of 6 times 7, which is 6 times 7 in the inside of the radical, and then minus the square root of 6. Okay, what do we have? 5 times 7. Well, actually, we have it in factor form, and we can tell there's no common factors that can be simplified, or rather perfect square that can be simplified. So this is just going to be the square root of 35. And then plus the square root of 5. 6 times 7, that's also okay. That's 2 times 3 times 7. And well, none of them are perfect squares. So we're just going to keep it like the square root, or rather negative square root of 42. And square root of 6 is just the square root of 6. So in this case, and you can see this very often times, we will just have a bunch of radical terms for which there's nothing to simplify, there's nothing to keep doing any further. All right. Let's have a look at something like letter C. Letter C, well, that's a product of two radical terms. All right, so of the radical terms, but these ones now contain variables, contain the x's. Okay, so that'll be okay. We're gonna do the same distributive property or FOIL, and that's gonna be, well, number one, 7 root of x times 3 root of x. And well, what's next? 7 root of x times, or rather minus 7 root of x times root of 5. So that's the result of distributing the first two. 7 root of x times 3 root of x. We're going to simplify the coefficients in a second. And 7 root of x times negative root of 5. Let's do the second part. The second part of the foiling here. That'll be, so that's 5 times, plus 5 times 3 root of x minus 5 root of 5. And well, that's as far as expanding this product. Now let's simplify this. Let's multiply the coefficients. 7 times 3 equals to 21. And then that's going to be square root of x times itself, x times x, and then minus 7 times the square root of a product between x and 5, have about 5x, and plus 5 times 3, it's going to be 15 root of x, and lastly minus 5 root of 5. Well, we may be able to simplify things a little bit here, but I don't think there's much to do. So just the x times x, which will be x squared inside of the radical, and then everything else just remains the same. 7 square root 5x plus 15 root of x minus 5 root of 5. All right, and well, the only term we can simplify is that first term. What's the square root of x squared? X. Just x, all right? Because in this case, this coefficient 2 is divisible by the index, which is also 2. That reduces to 1. That's 21x minus 7 square root of 5x plus 15 root of x minus 5 root of 5. And I don't think there's anything else we can simplify any further, because look at all these terms. None of them contain any like radicals. Again, radicals that contain the same, well, in this case, they all contain the same index, but none of them contain the same quantity inside of the radical. That is the radicand. All right. Okay, so for letter D, the 4 root of 3 minus 1, all quantity squared. Alright, so that's going to be, well, in this case, that doesn't look like a product of two binomials. However, looks like a binomial square. Well, that square really means that we can rewrite this binomial, 4 root of 3 minus 1, and multiply with itself as many times as the exponent tells us here, in this case 2. That is 4 square root of 3 minus 1. And then from here we can just follow the process we did with the previous examples. That is 4 root of 3 times itself and 4 root of 3 times negative 1. That is going to be, well, 4 root of 3 multiplied with itself times 4 root of 3. Then we'll deal with this in a second. And then 4 root of 3 times negative 1 minus 4 root of 3. Then from here, how about we do the second part of the foiling, that is negative 1 times 4 root of 3 and negative 1 times negative 1 equals to positive. Okay, so that's negative 4 root of 3 plus 1. All right. This dot product in the first term, 4 root of 3 times itself, that's going to give us number 1, 4 times 4, which equals 16, and then the product of the radicals, it's going to give us the radical of a product 3 times 3. And then, well, here we have a couple of like radicals or like terms because they have the same index in the radical and the same quantity inside of the radical, so we can combine those two together to give us a negative 8 root of 3, and then just bring down that plus 1. So here we're going to have the 16 times the square root of 3 times 3, which is a 9, minus 8 root of 3 plus 1. And in this case, well, that first term is going to give us a nice number because 9 happens to be a perfect square, which in this case is a number 3. Square root of 9 equals to 3, so that's 16 times 3 and minus 8 root of 3 plus 1. And then 16 times 3, which is 48, minus 8 root of 3 plus 1. And while there's only one radical term in here, all we do is just combine the integers 48 plus 1, and then from there subtract the radical term. That will give us 49 plus or rather minus 8 root of 3. And that's our final answer. All right? Okay, let's have a look at the last exercise from this set of exercises. That's the square root of 2x minus 5, the square root of 2x plus 5. All right. Okay, so for this last exercise, letter E, well, the square root of 2x minus 5 multiplied by the square root of 2x plus 5. And well, a lot of you do the following approach. You did the, what's it called, the FOIL approach, which I'm going to do. Let me do it. And then let me show you a shorter way to go about this one. So let's see. Okay, doing the FOIL approach, that's going to give us, okay, so the square root of 2x times itself square root of 2x. And then plus 5 times the square root of 2x, which is, and then, well, let's do the second part of the FOIL, that is negative 5 times square root of 2x and negative 5 times 5. Alright, so that's going to give us negative square root, negative 5 root of 2x, and then minus 25. Right? Now, right away we can see the following. We can see that these two terms are like terms. They have the same coefficient, however, they are opposite in sign, so we can cancel them out. For the first two terms where we multiply the two radicals, how about we multiply the square root of 2x times itself to x, and then minus 25. The 25 goes outside of the radical, by the way. So what is that going to be? 2x times itself, that's a 4x squared minus 25. And notice how the first term has is a perfect square, 4x squared. That is going to be reduced to 2x minus 25. In fact, not even a single radical appears in our final answer, right? So yes, this is the FOIL approach, which is fine if you want to do it like this. However, there's another way to simplify this one, because check this out. This is a special form. That special form, which is, okay, let me write it again, square root of 2x minus 5 times square root of 2x plus 5. Well, notice the form right here. I'm pretty sure you've seen this form before. So this looks like a lot like a minus b times a plus b. Doesn't that look like that? What is that?
Difference of squares.
Isn't that a difference of squares? So what is that equal to in algebraic form?
A squared plus b squared minus
A squared minus b squared, right? So instead of doing the whole foiling, check this out. What you could do instead is The first a squared, that is the first quantity a squared minus the quantity b squared, and that'll be the square root of 2x and minus b squared, which is 5 squared. And in this case, from properties of radicals that we did last time, the radical cancels the power, and that's going to leave us with simply 2x and 5 squared equals to 25, which is a way shorter method to go about this one. However, this one, you can do this shortcut in a way only if you have these radicals as a product of two conjugate binomials. Like, what do we mean by conjugate binomials? So these two are binomials because there are two terms. The fact that they are conjugate binomials, that means they have the same a terms and the same b terms. The difference is one is minus, one is positive. Special form, let's put a name to it. Product of conjugate binomials. All right, product of conjugate binomials. If you have them in that form, you can go ahead and do that. However, you might want to verify why it doesn't work for the previous exercise. If you try to do that, well, this one is not a. Although we have the same A and the same B and B here, they're both separated by a negative sign. If one of them were a positive, then you can do the product of conjugate binomials by using the reverse, in a way, the reverse of the difference of squares. The previous one, no, we can't even think about it because, well, although we have root of x and root of x, look at the coefficients. One is 7, one is 3, and although, well, this is a positive 5, this is a negative, but not 5, it's a root of 5. So we have terms and symbols like all over the place, so that doesn't even look like a product of conjugate binomials. All right. Okay, so let me